Welcome back, everybody. Our next activity is going to be to design our own simulation of physical motion using a tool that you can find openly accessible on the web to do generative art, um, which is sort of a somewhat niche movement to use software and code to create artistic works. But I found that any program that can be used to draw using code can also be used to make simulations. And so what we're going to do is we're actually going to simulate a ball dropping. I've tried to choose something relatively simple so that you could give students an opportunity to think about what's actually happening with the motion of an object as it falls through space. Now, we're going to actually take this into two pieces. When I start, I'm actually just going to do a simple example program so that you can get a hang for what's going on inside this particular programming language, which is very similar to what we used with the Arduino. And then after we do that simple program, then we're going to switch over and we're going to do the ball drop. Okay. So if you like just to jump right in, you can go ahead and fast forward to the ball drop. If you want to learn some of the basics of this platform, hang in here with me and we'll do a quick, very short program that shows you some of the capabilities of what's happening with this particular programming language. Okay, this is the website OpenProcessing.org. There is a programming language called processing, which is used to do generative art. And you can download a local copy of the processing editor and compiler. But there's also this online version. And the online version uses JavaScript libraries to do some artistic creation. Now, I will tell you that if nothing else, you should go to this website and look at some of the amazing things people have created. I used to, when I started using this myself, my college students were really excited because there was a band that they had all heard of who made, they basically wrote code to generate a bunch of graphics using this program. And then they used a projector to project it on themselves while they were playing music in a video. And some of the kids had seen the video. So that was kind of a cool thing. So we're not going to do all that, but I will show you how you can use this programming language to learn some things about drawing with code, and then how to translate that a little bit to something scientific in terms of simulation. So you want to click the button in the corner that says create a sketch. And so what you're going to see here is it gives you starter code, much like what you saw with Arduino. And it's got two methods or functions. Those words are mostly synonymous in terms of computer science. And the first function is called setup, and the second function is called draw. And so what happens in this programming language in this tool is that you run the setup function and it does it once at the start of your program. And then it runs the draw function on a loop. So it continues to do that. And this is the basic default code. So I will just show you what that does. If you click the play button up here, it will take you to a canvas and you can interact with that canvas. If you click this button, it takes you back to the code. So I'm going to click the play button. You'll notice it turns the background gray, and as I move my mouse around, it's going to draw an ellipse, which in this case is a circle, everywhere that I go. That's it. This is all this does. But it's kind of neat. And the reason why it does that is in the setup function, it creates that canvas, which is the size of my window. It sets the background, which is the color, using like a shade of gray, essentially. I'll talk more about how some of these functions, sometimes you can use them with one input, and sometimes you have multiple inputs that'll give you more flexibility. And I'll try and help you figure out where to find what we call the API, which helps. It's called an API, an application programming interface, and it's a list of predefined methods that you can use in your program. So I'll show you where to find information on how to use background, for instance, and how to use ellipse. So that's the setup. Then when we go to the draw function, which is run repeatedly, it's always going to draw an ellipse at the x position of the mouse, at the y position of the mouse, and it's going to be width 20, length 20, I think based on major or minor axis of an ellipse, but I'm not so worried about that. Okay, so we're going to take advantage of that. Now I'm going to do this real quickly because I want to give you an opportunity to see where you can get more information if you need it. Now, if you recall, we were using OpenProcessing.org. This is at the website processing.org. There's a subtle difference there. The reason why this website has the reference, which has all these different functions. And if I was to click here and scroll through, you can see there's a lot of functions you can use. So the more comfortable you get with this and the more of these tools that you learn how to use, you can do all sorts of really fun things. Now, we're not going to go too crazy here, but I do want to show off, for instance, the background, because that was one of the functions we were going to use. So it starts with some examples. It gives you a description of what the function does, shows you the syntax, and then describes the parameters. So you notice the version that they ended up using was this background gray, where gray is a floating point number and specifies a value between white and black. But we can change that, and so we can change it to use what we call RGB values, or we can specifically note the amount of red, the amount of green, or the amount of blue that we're going to use. So we're going to go back here, and I thought it would be fun just in terms of this introductory activity to do a couple simple demonstrations. So we can put any amount of red, green, and blue separated by commas up here. Now the scale of numbers goes from 0 to 255 because there are 256 different color values we can use in combination with one another. So let's say I want there to be no red, all green, which is 255, and no blue. So this should be a very green window when I run the code. Wow, that is very green. Now I'm a Michigan State Spartan at the moment, so this is somewhat appealing, although I don't think that's the right green. If you change these other values, let's say we want half as much red as is possible, roughly, and I run it again, now it makes this interesting shade, which I'm not sure I'm going to name, but you can continue playing with that. I think we should, let's get rid of that, and we'll go with more of a, let's see what happens if I add a little bit of blue instead. Oh yeah, that's much nicer. It's like a teal. Let's go with a teal. Now my draw function, what I'm going to do is I'm going to introduce some variables. Now, if you remember when we worked, for those of you who did the Arduino session, we had to define the type of our variable. We're going to create a variable that stores a random value for red, a random value for green, and a random value for blue. So 3 different variables. I'm going to call those R, G, and B. Okay, but here in JavaScript you don't have to specify a type. This is a point of contention amongst computer science people, because when you do specify a type, it helps protect you from making mistakes like assigning some kind of information you don't want into that variable, which would later break your program. And then the people who are like, no, just give me the freedom to do whatever I want. JavaScript lets you do whatever you want, sometimes to your benefit and sometimes to your detriment. So we're going to use a function called random. And in the random function, inside the parentheses, you specify the max value that you want, or the min and max value that you want the random number to take. As I mentioned earlier, the colors are range from values 0 to 255. So we don't have to specify the 0, but we do have to say 255. And then you'll forgive my laziness here. I'm just going to copy and paste this on these 3 lines. So now I have color values, RGB, and they're all going to be random every single time this draw loop iterates. Okay. Now what I'm going to do with that is I'm going to change the fill, which is the, no pun intended, I'm fill, but this fill function is actually the way that you can color a object that you're about to draw on the screen. So I'm going to fill that with a random collection of colors, and then I'm going to draw my ellipse. And just for fun, let's change this from 20 to say 40. If I run my code now, Look at that. Now I'm painting a rainbow of crazy colors in oval form. Okay. This is a silly exercise. I understand that this isn't much code, and I just wanted to do something like this to demonstrate to you the power of a tool like this. So this might be a fun early exercise to do with your kids, or something like this, where you draw some silly objects on the screen, just so they can get a sense of how they can manipulate things. And it gives them a chance to make some easy mistakes without long-term detrimental impacts. As I talked about earlier, sometimes when you write code, you run into errors. And when you run into errors, if you have a lot of code that you're trying to write at once, it's really hard to track down where that mistake might be. So you might want to start out with something simple with your students. I'll give you an example. If I do this and I take that semicolon off, actually, I don't know if this will make a difference. But it doesn't. All right, so this is a language that doesn't require the semicolons. So isn't that confusing? Anyway, something to think about. I'm going to take a break here, and when we come back, we're going to talk about our simulation. Hello, everyone. Phil back again. Now that you've had a chance to play with OpenProcessing, I thought it would be a good time to start working on our first simulation. Now, I am not an expert at physics, and I'm not an expert at science. So I chose something that I think is relatively simple. We're going to look at a ball dropping with regular gravity, and we're going to let it go and let it bounce. Now, admittedly, I think the extension for this would be to worry about what happens when the ball hits the simulated ground, which we're not going to do. I tried to keep it relatively simple for this first one, especially because we were just kind of learning how to use the tool. I will challenge some of my very smart folks out there in the crowd to take this to the next level. What we're going to do is we're going to write our starter code, meaning our setup code, and then we're going to write our loop. And we're going to have to handle the circumstance of when the ball hits the ground so that it goes in the other direction, and also that building up of acceleration, not building up of acceleration, sorry, building up of velocity due to acceleration, due to gravity. Okay, should be relatively simple. So let's get right to it. Okay, we're back on the OpenProcessing website. I kept my tab open with my reference in case I need it. I'm going to click on Create a Sketch again. This is a brand new sketch. So what I think I'm going to do first is some really easy stuff. Let's change the color again to something else. I just want, let's make it a random color. Let's go 145 and 32 and 198. I don't know what color that is, but I'm excited. Then we're going to type this line, which basically sets the fill to black, and we're going to draw a line. Now, basically what happens when we draw a line is we're going to provide a starting point and an ending point in two sets of coordinates. So it's like x1, y1, x2, y2. So my starting coordinate is going to be at position 0, and then we'll draw this one. You'll notice up here we actually have these constants, which we can use. So I'm going to draw this guy at the height of the window, minus 50. And then I'm going to do the other x coordinate at the width. And then I'm going to draw the other y coordinate, since I don't want the y to change at all, also at window height minus 50. Okay. Now, this is the beginning of the one really challenging thing that we're going to have to constantly reflect upon as we do this activity. And I had a big sigh there, because this is the one part that probably makes this this activity somewhat challenging to think about, which is we think of our XY axis as being centered, down at the bottom where the X's go these ways and the Y's go these ways, positive, right? But computers draw from the upper left corner of the screen. So we're flipping it upside down. And so that means when you increase your Y, you're actually going down. So just keep in mind that the Y-axis is reflected. okay? Hence, what I'm doing with my height of my window is I'm drawing it minus 50, which will actually put it at the bottom of the screen, okay? Let's just take a quick look and see how we did with our drawing. All right, now remember, it's still doing what the other program did, where it's when I move the mouse, it's drawing the ellipses in black. But if you'll notice at the bottom of the screen, it does have a line, and it seems to be this somewhat nice purple color. Maybe it's a little intense, the purple color. I don't know how well it shows up on the screen, so I might change that so that there's, I don't know, maybe there's less, of that, and maybe a little less red there. Let's go one way. Let's see. Is that a nicer color? Ooh, no, it's darker. If you ever want a very specific color, you can actually go and look these numbers up online, and that could be really helpful. Maybe the key is I need more green. Let's try that. All right, now I've got this color. I don't know what it is, but that's okay. Okay, so this is the start of my program. Now what I want to do next is I need to set up my initial variables. So I'm going to have these variables that are basically going to keep track of the various parts of my program. So I want to have, let's see, we're going to have a Vx, so the velocity at any given point in my program. We're going to have an acceleration. We're going to have a time. We're going to have an x, and we're going to have a y. Okay, those are the things I think I need. Now, if I was designing this program from scratch, I might not know that I need those things. So keep in mind, I've done this before, and I'm trying to save some time. So this is based on my understanding of the math that I'm going to end up using. And if you want to do this with your students, what you might do is you might start by introducing the equation. So let's skip this ellipse thing for a second. In fact, let's not worry about the ellipse. The double slashes means comment a line out, which means that the code will not be read by the computer. It won't be executed at all, it'll be ignored. It sees the double slashes and says, I don't care what you type afterwards, I'm going to ignore it. Keeping that in mind, I'm going to type in the equation that I know that allows me to know the y position of an object being dropped. I know that my y is going to be the initial y plus the initial velocity times the time plus, and there's a reason I'm putting plus there, physics people, don't get upset with me yet, half the acceleration times the time squared. That's basically what I want to do, okay? So again, I need to make sure I have those things, but another equation that I'm going to use that I know of, thanks to the internet, again, science teachers, don't get upset with me, is the x at any given time for the velocity, excuse me, the velocity at any given time is the initial velocity minus the acceleration times time. Okay. Those are the things that I can use. And so I'm going to use those throughout my program, and that kind of informs the setting up of variables. Now you might be saying, well, Phil, I see a bunch of initial y and initial velocity, and there's more to it. Obviously, I need to take some other steps, but let's start with this for now. Now, up here in the setup function, we can set our initial values. When I start my program, my velocity is going to be 0. My acceleration is always going to be negative 9.8 meters per second squared. My time can start at position 0, my x can be at 0, and my y can be at 0. We'll just give them some initial values to start off. Okay. Now, I'm going to add one more variable up here, which I didn't really talk about. This one is important, but we're going to end up using it for the purpose of controlling the action in our program. So I made this variable called released. And what I mean by that is I'm going to use the mouse to hold the ball, and at some point I'm going to release it. When I release it, we're going to start the simulation. Okay, but until I release it, released equals false. And again, false is a Boolean value that just means 0. Okay, true means 1. And the computer uses that to keep track of whether something should or should not occur later in the program. Okay, so that's pretty good. We've got to start now. What we need to do is we need to start thinking about how we're going to structure our program. And one of the things I like to do when I'm trying to figure out what I ought to do, in addition to making comments like I have here, is I actually like, and I'm going to get rid of the ellipse part here, I like to write what we call pseudocode. So I like to actually include notes inside my program. So what do I need to have happen? Well, I need to ask a question. If the ball is released, we're going to do one thing, and then otherwise we're going to do something else. Okay, so that's the first step, is I know that that's going to happen. And based on those two possible outcomes, I'm going to determine whether I'm dropping the ball or if I'm just going to do a simple update on the screen. And so then at the end of the program, I want to draw the ball. Okay, and I'm going to put draw the ball / refresh the screen, because one thing you might want to talk about with your students is the idea of animation. You know, we're not going to animate something on top. The reason why that program that we did in the example program worked the way it did is because we were constantly drawing on top of something. But in this program, because we want to show the ball changing, we're actually going to redraw the screen almost like it's a cartoon every time. So that's going to be the final part. Now, I think the if the ball is released part is the most complicated. You know, obviously we're going to start using our equations in there. So I'm going to take those out and I'm going to put them inside here so that I'm ready. And I'm going to put them in as a tab just because that'll give me a little bit of like a, it allows me to kind of see where my code will ultimately lie. The otherwise is actually pretty easy. So I'm going to write that really quick. What I want to do is I want to draw the ball where the mouse pointer is. Okay. And then here we're going to have to do a couple updates, right? We're going to have to, always we want to update the time, right? Because the time is going to be, once we drop the ball, the time's going to start. So we need to update the time. And we need to, let's see, update the Y, and then we need to update the VX. I think those are the three things that we should need to do every single time based on our equations. And there's one other thing that I'm going to do, and now I didn't know this when I first wrote this program, but it is something that's important. So what I'm going to say is I think the last thing we need to do is check if ball hits ground. If so, deal with it. Okay. So these are kind of my steps. This is the algorithm development process. This is me using my brain to try and figure out what I ought to do. Okay. And this is pretty good. So this is what I need to have happen in the draw function. So now I can start writing my code. Now what I'm going to end up doing is I'm going to replace some of this, these comment lines with real code. So the first thing I said is if the ball is released. Well, we ask a question really easily. We say if, in parentheses, we put a Boolean value. Now you can say if released equals true if you want. And that's pretty explicit, meaning like it's easy to read. If you use one equals sign in programming, it means assignment, which means set the thing on the left equal to the thing on the right. But if you use two, it means compare. Are these two things equal? Released, the variable, can only hold true or false. So right now, remember when we start the program, it said false. So it's going to say if false equals true, which is not correct, then it'll skip everything that's in the brackets. Okay. But as I say down here, otherwise, we say else. And when we say else, we can put another curly brace and then do the thing that it's supposed to do inside the else's. Okay. Now, obviously, once you transition from writing code using these little comments, which don't do anything, to writing actual code, it can start getting cluttered. So I will get rid of things so that way it doesn't look so cluttered and it's easier to read as I go. You can leave them if you like, but I'm just telling you what I prefer. Okay. So I'm going to do the else condition first because it's actually a lot easier. It's very similar to the way that we had it before. Where basically we're going to say, let's set the x equal to the mouse x, and let's set the y equal to the mouse y. Okay. Mouse x and mouse y are built-in variables. So these will always keep track of where those two positions are as I move the mouse around the screen. And if I assign them to X and Y, I can then use them when I draw the ball and refresh the screen down below. Now to do that, I'm going to do something like I did when I did the Arduino exercise. I'm going to write a function called update the screen. And I'm going to send it a couple pieces of information. One is I'm going to send it the X value, and then I'm going to send it the Y value. And there's one more thing I want to send it, which is, it'll become important later. Actually, let's just leave it this way for now. Okay, and then we'll show you how to make a change later. Okay, then I'm going to say function update screen, because now I have to define it. This is not something that's built into the program. Oops. And now I have a function. Now it doesn't do anything. One thing though is that we want it to redraw everything. So I'm going to go back up here and I'm going to take care of this part of it, which is where it sets the background color, it sets the fill to black, and then draws me my line. I want that to be reproduced every single time, so I'm just going to put that right at the top. Okay. Now, the next thing I want to do is I want to draw the ellipse at position X, Y, and let's just make it the same size as it was before, 2020. Okay. Now I'm going to run my code right now, just to make sure everything's working okay. And what you'll see is now I've got a ball that just follows my mouse around. Okay. And that's because I'm redrawing the screen every time. But it's essentially very similar to what I had been doing before. When you're working with kids on code, it's helpful to do a simple set of steps like this to start, because this is an accomplishment and you can celebrate this. You have a ball that now follows your mouse around and it doesn't leave a trail. You did that, okay? That's a big step. Let's take a pause and then we'll come back and we'll work on the next part of our code. Okay, now we have a screen in our simulation that allows a circle to follow our mouse pointer, which, like I said, is a success. But our next step is we want to actually be able to drop the circle like a ball and see if what will happen when it hits the ground. So we're going to go ahead and start working on that. Now here's our ball that follows our mouse pointer. Here's the code that did it. So we're going to add some stuff because all that's happening right now is this code inside here. We haven't really dealt with this idea of releasing the ball. What I'm going to do is I'm going to add another function. This function is going to be called mouse clicked. Now I'm going to let you in on a secret of programming, so you're getting some exciting advanced inside knowledge here. When you write a program that has interaction, what happens is the program itself has to have what's called an event listener set up. It's basically like the annoying kid in the back of the car when you're on a long family vacation. It just keeps asking that question. Did you click the screen yet? Did you click the screen yet? Did you click the screen yet? And as soon as you do, it'll do whatever is in the function that is associated with that event. Now there's a predefined event called mouse clicked. So we're going to write our own mouse clicked function. And inside, the first thing we're going to do is we're going to say released equals true. Now be careful, here I used 1 equal sign and here I used 2. Up here it's a comparison, and down here it's actually assigning the value true to the variable released, so that when we use it in the future, that's what it'll do. Now what I could do, if I wanted to be real clever here, is I could set it up so that I could release it and then click again to start over. But let's save that for another time, okay? Now the other thing I want to keep track of here is I want to set my initial Y value when I click the button to mouse Y. That's basically so that I have that stored for all my future calculations. If I keep changing the Y variable, I won't know where it originated. So I want to make sure I have that stored somewhere. Another little side comment here, the spaces in between things like equal values don't matter, and you can have a bunch of spaces in between the when it compiles, it looks for patterns, and that's what those programs do. Is they're very complicated. They look for patterns, and they can handle some of the variation there. The other thing I'm going to do is I'm going to set my initial velocity, which was already set to 0, but just in case, let's set it back to 0. Okay. Now, when this part of the program loops, it has some things set so it can start doing what's inside here. Okay, so that's pretty exciting. So now we can use the formulas. Okay, so we're going to update those two using the formulas. So I'll get rid of those 2 lines there, and we can write that equation. I don't know why I double indented. I apologize. Okay, so now I can actually write this statement. It's going to look very similar because I named my variables the same things. There's a slight variation here. The asterisk is the multiplication. Oops. That's my acceleration. Now, here's the thing. There is no caret symbol like you used to use on your old calculators, your TI-80, whatevers. There's no caret symbol meaning exponent, not in programming languages, not most programming languages. Instead, you can use built-in functions to do exponents. But what I'm going to do here is I'm actually going to just do I'm going to be literal. I'm going to literally multiply t by itself. Okay, and that is my update for the y position. Then I want to update my current velocity by using the initial velocity and subtracting a times t. Now, for some of you, you may say, like, hey, these lines are similar. I don't need this information anymore. Great, let's get rid of it to clean up our code so it looks nice and neat. Okay. Now, there's one other variable I haven't updated yet. I'm using t. It started at 0. Seems like I should start updating it. So we're going to change t. I'm going to change it by tenths of a second because I kind of like that slow motion action. And keep in mind that you can change this throughout the course of writing your own program. So as you're doing this with the students, you can set it so that it goes up by 1 initially and it'll move real fast. Or you can set it to 0.1 and it'll go real slow. But there's a caveat to this. And that caveat is we need to set the frame rate. Now the frame rate is how many updates the program will do per second. How many times will this draw function be called per second? The default is like 30, okay? But if I've released my ball, I want to make sure that the frame rate changes. And let's do it 10 updates per second, because 10 updates per second, where every update is going to be 1/10 of a second, should match up, okay? So now I've updated the time. And let's not worry about the ball hitting the ground yet, okay? Let's just run and see what happens. And I want to stress this too, because now we're getting into some like heavier coding than what we've done in other projects and other programs that I've written with you during this brief time we've known each other. And I really think it's important to do this process, which I call code a little, test a little, code a little, test a little, because the more code you write in one fell swoop, the higher the likelihood that you're going to get an error, and then the harder it's going to be to track down the error. So if you just do it in little increments, you might have more success. So let's see if this works. All right, there's my ball. Everything's cool. I'm going to click my mouse. Okay, so something's happening. Now I'm going to be honest with you. Not real psyched that my ball went up. I really thought it was going to drop down. So clearly I have made a mistake, which is okay, you know, and that's part of the reason I say code a little, test a little. We got to figure out, why did my ball just go straight up? And some of my science people were probably saying, as soon as I typed it, hey buddy, it's not plus 0.5, it's minus 0.5. You're subtracting the acceleration. Oh, okay, did I make a mistake? Okay, sure. Let's see if that does it. Now, it might not. Maybe that's just my simplistic approach to solving the problem, and I'm wrong. But let's see if it makes a difference. So we're going to run my program. We're going to move the ball around, and I'm going to drop it. Hey, look at that. That ball is really moving. Okay. Now, of course, that line is just a line, so it's just going to keep going right through it. There's no ground anymore. So we've got to worry about what happens when it hits the ground, and that's going to be our next step. But I'm pretty excited about the quality of the program we just wrote. And I think this is a time to do a little back patting, a little championing of our success. You are awesome. You did that. And let's pick this up in another session. All right, gang. I'm glad you're still with me. And I'm assuming you're still with me. We've been doing pretty well. Now we've got to worry about the ball bouncing back up. And again, we're not going to worry about elasticity or any of the other factors that impact it from a physics perspective, because I'm not smart enough yet to understand how to do that. But I am smart enough to finish a ball bouncing, which I think will be fun for the kids regardless, and might lead to some interesting questions. So let's go and make those changes to our program so that the ball bounces up. And then maybe we could even put some information on the screen so you can start to collect some data. Here's the code that we had written from last time, and we're going to need to make some changes. So this is where you got to get real creative. Okay, you got to really start thinking about another set of code. So if the ball hits the ground, what really needs to happen? This is where you got to get your brain active here. What changes if the ball is falling downwards to the velocity? My physics people probably know, and assuming a perfect system in which there's no loss of energy or anything else that's happening when the ball collides with the ground, what would happen? Well, that vector of the velocity would go the other way, right? So one easy thing we can do is we can actually start the whole system over again, okay? When we start that system over again, we can change the velocity by reflecting it. So that's what we're going to do, is we're going to reflect the velocity. We're going to restart the timer, and I'll explain why. This is a little bit of a cheat on my part. I think if we were being more clever, we could figure out a way to keep the timer going. But for me, based on the fact that I'm using these equations up here, I thought, you know what? If I just restart the timer, then this calculation will remain correct. Based on the way that I think we're going to approach this. So let's make sure that we're restarting the timer. And again, as you get more comfortable with this, you can maybe take the program to the next level. But let's go with the simple solution first. And then lastly, well, no, let's not do anything else just yet. Okay, but let's write this conditional statement. So if something happens, which means the ball hits the ground, let's not write the condition yet. Let's just say we know it's going to be if that happens. Then we can reflect the velocity. I can write that. Let's reflect that velocity. That's going to be easy. Okay. That means I take my initial velocity and I'm going to set it to the current velocity, except now I'm going to multiply it by -1. Reflect it. Check. That's pretty easy. Then I'm going to restart my timer. I take my timer and I set it to 0. Done. Now, one common programming error is when you start a curly bracket or curly brace and you don't close it. I sometimes call these birdie braces because they look like a real crude drawing of a bird flying through the sky. I don't know, just me. Okay, so I've got my block of code that's going to happen conditionally if it hits the ball. But look at this. Even when I hover over it, it says expected an identifier, expected something. You don't have to worry about what that means, but you know it's a problem. All right, so I got to figure out, how do we know that it's hit the ground? Well, one thing I do know is I have the y value, right? I've updated it on line 19 here. And the y value is my current position in the y dimension. So the ground, if you remember correctly, was a line I drew. And if I look up above, I know that that's when the window height was -50, or window height -50. That's the point. So I somehow need to compare those two values, window height -50. And the question, this gets back to what I was talking about earlier about the way that things are drawn on the screen. Remember what I said, it basically reflects our y-axis. So even though in my head I'm thinking if the y is below that point, what I have to think is, no, it's if y gets bigger than that point. So I'm going to go ahead and do that. I'm going to say if y is greater than the window height -50, then let's reflect it and see what happens. And like everything I do here, I've coded a little bit. So now it's time to test it. And let's test it from close to the action here. So I drop my ball. I'm so excited. I'm so excited. I'm so excited. Okay. That kind of worked. Now it's going higher than it originally was. So somewhere in there, something got a little wonky, right? That is a little weird, right? But it is at least detecting that it's hit the line and it's bouncing back in the air. Okay. So now we just got to figure out, why in the heck did it do the thing it just did? Well, one thing is an idea that I didn't really talk about, which is the Y position, because we're changing it on this line, it's not just that it's greater than that point, it actually could also be much greater than that point. So one thing we might want to do is we might want to reset that value so it's the same as that window, or that line, excuse me. So now I'm going to reset it so that now the position is right there. That might make a little difference. Let's see what happens. I'm going to test it, drop that ball, and okay, that's a little bit better, right? It seems like it's going about the same height. Now it still goes below the line. And the reason for that is no image in our drawing is actually, it doesn't have two dimensions. It's really just a center. And the center is right in the middle of that ball. So when I'm testing the Y value, I'm testing the Y value of the middle of the ball. If I know how big the ball is, I can change my check. So instead of being minus 50, I want it to be minus 60 because I want it to be the line plus the 10 that goes to the center of the ball. And I'm going to do the same thing here. Let's see if I've got a good piece of code. I'm going to drop that ball. I'm so excited. That looks a little bit better, but not perfect. Maybe I made a mistake somewhere else, but it looks a little bit better. I like this. And now it's really working, right? This is pretty exciting. This ball will bounce forever. And again, that's where you can take the opportunity to take that to the next level. Maybe figure out roughly what percentage of the velocity should be lost. You don't have to multiply by -1, maybe multiply by -0.6, maybe multiply by -0.4. And then you can get the kids to start thinking about what that actually means. Pretty cool from a simulation standpoint. I've got one more thing for you. Now, this takes a little bit more work because it's a little bit less specific to code and thinking about problem solving and more specific to this particular programming language and the way it does things. We're going to try and write some statistics about our experiment onto the screen because that would be really cool. So we're going to go back to the update screen function. And the last thing we're going to do is we're going to basically, let me roll, get my comment up there. Let's do the commenting thing again. So I'm going to say, what I want to say is if the ball has been released, report stats. Okay, so what does that mean? Well, let's print out the time and the velocity. You could also print out the acceleration if you wanted to demonstrate to students that the acceleration isn't changing. That could be cool. But it's not changing. But if it's important to you, yeah, let's include it. Time and the velocity and the acceleration. Sure. Okay, well, so let's start writing the code. So it says, I wish I could actually bring this a little bit higher on the screen. I apologize for that. So it says if, and we're going to do the same thing, if, and we're going to put our curly brace, and this time I'll be smart about it, and I'll put the closing curly brace. So if the ball's been released, how do I know if the ball's been released? Oh, easy. I say if released equals, because it's a comparison, true. And then I got to do my printing. And this is the part where it gets real stuck in the muck in terms of like the language of using processing and drawing. So I'll just give you the clunky part, which is this. We're going to say text size. Let's make it 20. And then let's say text. Oh, not test, text. And then we're going to put something in here. And what we need to do is we need to put the string that we're going to, of text. Now, string is a string of characters, a collection of characters. It's a programming word, string. So we're going to put the string in, and we're going to have to create that string. And so we'll do that in a different step. Then we got to figure out where to put it on the screen. I'm going to say, it's just a guess, maybe a guess informed by my previously writing this program. Let's set it at window width minus 250 as the X and the Y. That should be the upper corner of where it's going to draw this. And you know what, if since I'm still in the testing phase, let's just put the word, this is my string. We got to put it in quotations. I'm going to say hello. Let's just see what happens. So no text right now. I'm going to move my guy right here just for a second. And then I'm going to drop that ball. See, I put the word hello up there. Cool. Okay, let's go back and change our text. So now I want to print out the velocity, the time, and the acceleration instead of saying hello. Okay. So I'm going to create a variable s. I'm going to replace the word hello down here with the variable s. And I'm going to build a string. To build a string means to concatenate. That's another programming word, concatenate. We're going to group strings together, almost smush them together. Okay. So the first one is going to say T for time, colon, space. And then I'm going to convert the time value to a string. And then I'm going to put another string together that says S for seconds. And then I'm going to do a funny thing. I'm going to put /n. And the reason I put /n is that means new line, /n. Let's not worry about that right now. Okay, just type /n for me. Now let's run our program. Ooh, I don't know what I just did. Let's close that for a second and see if the program still works. Oh, look, it's putting the time up there. Now, this reveals a really interesting thing about programming. When it comes to floating point numbers, which are decimal values in programming, they're always rounding errors because it actually uses a system of twos. It's a binary system, so it has a real hard time with the things that we think of as round numbers, which are based on a decimal system. So we can actually fix that. That's an easy fix, and I'm going to take care of that right now. Instead of just doing the string value t, I'm going to round the value of t to 1 decimal. Let's see if that makes a difference. Oh, I did that. Whatever I did again, I did it. Okay, let's just ignore that for now. Look at that. Those are some nicely formatted strings. And then it resets it. Okay, cool. Yeah, looking good. Let's add the next one. So when we do this one, what we're going to have to say is s equals s plus. So it's going to take this string that I already created, and then it's going to use the plus sign to mean concatenate. So we're going to add a second string. And this one, what I'm going to do is I'm actually going to type, let's do the velocity. Let's make it a string. Let's round it, just like we did before. And that was what was it, Vx? I think it was the Vx. That's what I want, the current velocity. And then what is that measured in? Oh, good conversation for the kids. I think it's meters per second. Let's put the /n so that we get another new line. And I know that you're getting bored of listening to me talk, so I'm going to hurry up and I'm going to do the last one. Acceleration plus string round A1. That's actually not necessary. You can think about it and tell me why, but I think it's good. And we'll say meters per second. And here I can write whatever I want on the inside, so that'll be good. I actually don't need that /n, but I'm going to do it anyway. Okay. I'm so excited for you to see the final product. Let's see it. Here's my program. Let's drop it from here. Look at that data. I'm so proud of us. Aren't we the best programmers ever? This is amazing. Your kids are just, their minds, their little nascent brains are just going to be blown because when they do this, this is going to be the coolest thing that they've done all day. Better than math class, better than gym class. I mean, maybe a kid hit the winning three-pointer in the basketball game in gym class, maybe. But I'm going to guess this is the coolest thing that happened all day. Okay, this is all I've got for you in terms of simulation, but I'm hoping that this kind of idea will help inspire you to create your own simulations for other things in class. And if you come up with something great, you got to tell me. Okay, I'm going to put my my information up for you again, and I'm going to encourage you to send me an email or hit me up on Twitter, and we can talk more simulations. Okay, I'll see you next time.